You might have heard that the safest way to get around the planet is to fly. The Federal Aviation Administration estimates that there are about 30,000 flights every day in the US, and the number of accidents every year is in the single digits, and even that number is getting smaller. In most years, fewer than 1,000 people die as a result of flying in the world. By comparison, deaths from car accidents in the US alone, while declining, still topped 30,000 in 2012. Worldwide, the number tops 1.2 million. The most dangerous part of your trip is the drive to the airport. It might not feel that way, however, when you're flying through a storm or even in clear air and the plane is being jostled by turbulence. Despite the safety of flying, did you know that we have yet to truly understand and predict turbulence? We still don't understand the nature of chaos. It's no coincidence that we can't yet predict the weather with 100% accuracy. The equations that describe the real, ever-changing behavior of fluids, air in the atmosphere and water in the ocean, have yet to be solved. Some physicists and mathematicians wonder if a solution is even possible, and suspect that weather and waves might be inherently unpredictable. Yet fluids in motion factor into so many aspects of our lives, from major events like storms and tsunamis to humdrum everyday applications like the fuel efficiency of cars. The first step to discovering a solution to a problem is to define what we do know, so that we can find the boundaries of what we don't. And we know enough to get around our atmosphere and oceans. So how do we navigate these unpredictable fluids? Airflow and lift are not the only forces at work allowing planes to fly. Yes, it was Bernoulli's equation that gave us a critical insight, namely that the difference in airflow over and under the plane's wings creates a situation in which pressure on the underside of the wing is greater than the top of the wing, generating lift. And of course, the thermodynamics of the jet engine power the differential airflow across the wings. But once we are in the air or on the ocean, how do we get to our desired destination, and what causes those bumps along the road? When the object we're interested in, for instance our airplane, is moving through a fluid, the air around it, how can it best be powered? And what are the unique challenges of navigation in fluids? This is where thermodynamics meets fluid mechanics, and concepts such as thrust and drag come into play. In today's lecture, we'll explore the nature of those concepts and what roles they play in moving us around the Earth. I think you already have an intuitive appreciation of these forces, even if you haven't used their official scientific monikers yet. Thrust is the forward force that pushes or pulls the object through a fluid. Modern airliners achieve thrust through the use of jet engines, which, you'll remember, force air to stream through their cylindrical design. But thrust can also be generated by other means. The space shuttle achieves thrust with the explosive fuel in the rockets attached to it during takeoff. Appropriately, they're called thrusters. Birds generate thrust by flapping their wings, and hang glider enthusiasts, well, they generate thrust just like Fred Flintstone did with his Stone Age car, with their legs by running off a cliff. Drag is an opposing force to thrust. It's the friction that opposes the motion of an object through fluid. In the case of objects moving through air, it's sometimes referred to as air resistance or aerodynamic drag. You've probably heard people say such and such sports car has a sleek aerodynamic design. Technically, that means that the shape of the car was designed to minimize drag. As an aside, yes, there is hydrodynamic resistance that acts on objects moving through water, which is why speedboats are designed to be sleek as well. As you might imagine, as thrust increases, so does drag, as these are opposing forces. So an airplane needs thrust to exceed drag in order to accelerate in a forward direction and generate lift. How do we reduce drag so that we can get off the ground? Drag depends on a few factors. As I alluded to, one factor is speed, As speed increases, so does drag. Why? More air molecules will strike against the moving object per unit time, so the force of these air molecules will contribute to the drag that opposes the thrust. Two other factors are the area or size of the moving object and the density of the fluid or air. Larger, more voluminous objects generate more drag than do smaller objects, as the larger object gets in the way of more fluid molecules than a smaller object would. Hence the sleek design of cars and boats to reduce drag. Similarly, an object moving through a high mass density fluid is subjected to more drag than is an object moving through a low density fluid. Imagine the drag of swinging a baseball bat in a swimming pool compared with swinging that bat in the open air on the baseball diamond. As it turns out, drag is an awfully complex phenomenon. It's an intuitively simple construct, but the closer you look at objects moving through fluid, the more varieties of drag reveal themselves. We've discussed a few factors that contribute to drag. Now let me briefly outline 3 types of drag: form drag, skin friction drag, and lift-induced drag. Form drag is the drag created by the general size and shape of the object. Again, a sleek, low-profile sports car generates less form drag than does, say, a van or a big rig, largely because the contours of the body design minimizes airflow obstruction. Next, skin friction is the drag created by the fluid molecules in contact with the surface of the object. Some objects have surfaces that are more resistant to fluid flow than others. You don't want shag carpet on the surface of your car. Seriously though, engineers are always coming up with less resistive materials. Competitive swimmers, for example, sometimes use full-body swimsuits with materials that generate less skin friction than the other surface material, which is human skin. Lastly, there is lift-induced drag, which is a phenomenon resulting from the redirection of the air at the rear of a wing, a region called downwash. Let me explain. As a plane begins to take off, its wing is not perfectly horizontal, but rather is tilted so that the forward-facing side is slightly elevated. This front-to-back tilt of the wing is called the angle of attack. Now, as the wing is thrust forward and the air flows over and under the wing, the redirection of the air across the wing is now not just the difference in flow rate across the top surface and underside of the wing, but also a deflection downward. It turns out that increasing the angle of attack also increases the lift because it magnifies the difference in airflow rate across the top side and bottom side of the wing. But it also increases the form drag, so more thrust is needed. One mathematical concept that ties together these various forms of drag is called the drag coefficient. The drag coefficient incorporates the main forms of drag into one simple number. Without going into the mathematical equation, the drag coefficient includes in its denominator the mass density of the fluid, the speed of the object, and the area of a reference surface of interest, such as the front of the wings or the bow of a ship or the front of a car. All the factors that we've discussed influence the amount of drag that opposes the thrust that is generating lift to get our plane off of the ground. The drag coefficient is never a perfect description, but it can be used to compare the drag generated by a variety of different objects, everything from planes and cars to bicycles and buildings. In general, the higher the drag coefficient, the more drag creating is the object. So, how does the drag coefficient of an airplane compare to, say, a typical car? Its drag coefficient is generally half that of a typical car's, so it's quite aerodynamic, as we say. A car's drag coefficient is half that of a tractor-trailer big rig, which in turn is less than that of an upright bicyclist. Now, of course, if you're in the Tour de France, the bicyclists can change their drag coefficients by crouching down, reducing the form drag. So we've covered the basics of the four forces which constantly act on an airplane while in flight. The wings, acting as airfoils, produce an upward force called lift. Acting against lift is the force of gravity. Because the plane has mass and therefore weight, gravity pulls it downward. Thrust is the forward force that propels the plane in the forward direction, typically by a jet engine or a rotating propeller. And drag is the air resistance that opposes the thrust, working to slow the airplane down. We've been talking about how an airplane flies under near ideal conditions, but as I alluded to at the beginning of the lecture, the real world is more complex. There are weather patterns to consider, geological features to obstruct wind currents, which of course can lead to turbulence. Experiencing turbulence when flying or when whitewater rafting gives us a direct sensation of the chaotic fluid dynamics around us. What's actually happening? You may recall that we encountered the word turbulence in the first lecture on fluid mechanics when we described different types of fluid flow movements. There is steady flow, or the uniform movement of fluid particles at constant rate and direction, and then there is turbulent flow, or the erratic, irregular movement of fluid particles. These terms apply to the air through which planes fly too. So when we think of airplane turbulence, we're referring to the conditions through which the plane, or the wings more specifically, are passing through. Erratic or changing air currents. Given our discussions of the forces of lift, gravity, thrust, and drag that act at all times on a plane, I think you'll appreciate how erratic, turbulent airflow across the wings results in a bumpy ride. As a plane flies, the airflow rates under and over the wings, if altered in variable ways, will produce subtle variations in the lift and drag. Rough air, as it's called, commonly occurs as a result of changing air current and weather patterns, like storms, which have updrafts and downdrafts that can act on the plane and push it up and down. Pilots generally steer clear of the storms by flying over or around them, but geological features can disrupt airflow as well, creating turbulent conditions. Now, if you've ever flown across the US, you probably experienced some bumps flying over the Rocky Mountains. That's because the air sloping up and over the mountains creates mountain waves, or turbulent flow, much like water breaking on a pier or a coral reef. And finally, the global jet streams, the continuous airflow created by tropical and polar air currents, have an inherent variability as well that contributes to turbulent air. All told, these multiple factors give navigating in midair an inevitable factor of unpredictability. But the next time you're flying, keep in mind two additional points. First, airplane design and construction can withstand an extraordinary range of stresses on the plane's body, far more than what it is subjected to during typical turbulence. So, structurally, the plane is safe. Second, the statistics tell of an exceedingly small risk of bodily harm due to turbulence. Of the tens of millions of passengers that fly in the US every year, there are roughly 50 or so turbulence-related injuries, and usually these are sustained by flight attendants or passengers who were caught without their seatbelts on. That's 0.000001% of passengers, an infinitesimally small incidence rate. Try to remember these points and principles of fluid mechanics when your heart rate jumps during a bumpy flight. It doesn't always work for me, particularly when my instinctual fears kick in, but sometimes it helps. What makes fluid mechanics such a fascinating area of study is that the principles apply to so many aspects of our daily lives. I'd like to describe three more: acoustics, hydraulics, and plasma physics. First, let's talk acoustics. When you hear the word acoustics, it probably calls to mind a concert hall or an electronics store selling stereos. So we associate acoustics with hearing, sound, and sound quality. And yes, that's largely what acoustics is all about, but technically, acoustics is the study of mechanical waves in any medium, be it gas, liquid, or solid. Since fluid mechanics deals with the properties of materials that flow, acoustics is actually considered a branch of fluid mechanics. If you recall from Lecture 8 on hearing, sound is the spectrum of pressure waves, waves that have both amplitude and frequency, which propagate through compressible fluids such as air or water. Our sense of hearing is possible because our inner ears are equipped to pick up small oscillations in air pressure that we then perceive as sound. As we heard in Lecture 8, neuroscientists define sound as perception, and they believe that if a tree falls in the forest and there's no one around to hear it, it doesn't make a sound. But I want you to remember that pressure waves generated at the time of impact do propagate through the air outwards, irrespective of whether or not a human or a squirrel or anything else is close enough or sensitive enough to register that sound. Going back to our flying plane, I'm sure you've seen a few of your fellow passengers with fancy noise-canceling headphones. How are these different from standard headphones, and how do they work? Standard headphones operate similarly to most typical speakers. They emanate sound, reproducing the vibrations of air pressure oscillations to approximate the recorded music or speech. Noise-canceling headphones, however, have a twist. Their purpose is to prevent unwanted sounds from entering the ear, thereby producing a higher fidelity aural experience. How might they accomplish this? Because sound is merely the air pressure changes of a certain amplitude and frequency, these headphones introduce another source of air pressure changes that are equal to and opposite of those coming from the unwanted noise source. When, in an ideal situation, the two match perfectly but oppositely, the human eardrum will not register any sound because there are no net pressure changes to cause vibration of the tympanic membrane in the inner ear. The waves cancel each other out. This is what noise-canceling headphones do. They literally cancel out or nullify unwanted sound waves, say coming from the jet engine or the conversations of people around us. To accomplish this feat, they use an embedded microphone to pick up ambient noise around the listener. And using electronic circuitry, they transform that ambient noise quickly into opposing sound waves. As you might imagine, this electronic process is fast, but it's not instantaneous. So low frequency, that is lower pitch sounds with fewer cycles per second, can be better canceled than higher frequency or high pitch sounds. It's a lot harder to cancel out the baby's cry than the low rumble of the engine. But all in all, it's a very elegant product that utilizes an understanding of both fluid mechanics and human auditory physiology. What about sound underwater? Underwater acoustics follow the same basic principles as airborne acoustics, but of course, the properties of the fluid through which the waves are propagating, the water, come into play. One very important difference between air and water is compressibility and its inverse, elasticity. Remember in our last lecture, we touched on compressibility when we discussed the effect of pressure changes on the volume of static fluids. In general, water is rather incompressible, whereas most gases, air included, are very compressible. Think about the can of compressed air that is sometimes used to whoosh out the crumbs from your computer keyboard, or the surprising weight of a propane tank that you use in your grill or heat lamp. In both cases, those items are filled using high pressure to compress more and more gas into the container, and the relative compressibility of gases allows that to occur. Now think about water. When filling up a jug of water, it's pretty tough to stuff more water in a given volume. The water is nearly incompressible. So what does this have to do with sound? Well, it turns out that the speed of sound is highly dependent on the compressibility and density of the fluid through which the sound waves are propagating. The less compressible a substance, the faster sound travels through it. In general, the speed of sound is higher in solids than in liquids, and it's higher in liquids than in gases. Why should this be? Compressibility is just the inverse of elasticity. Liquids are more elastic than gases, because when molecules in those fluids are moved from their starting position, there is a restoring force to get them back into position. There's almost no restoring force in gases like air. So you can think of the path of sound like a rock in a slingshot. The stronger the rubber band, that is, the elasticity or non-compressibility of the medium, the faster the stone, the wave energy, will travel once it's released. So with this in mind, though water is denser than air, it is also much less compressible. So sound travels 4 times faster in water than it does in air. The speed of sound in water is approximately 1,500 meters per second, while the speed of sound in air is approximately 340 meters per second. This relationship between sound travel and compressibility of the medium or fluid holds true for other materials as well. Sounds travel faster when propagating through the steel rails of train tracks than when propagating through air. We can hear the train coming along the track if we put our ear next to the track well before we can hear its engine in the air. The incompressibility of water and air come into play in other applications of fluid mechanics: hydraulics and pneumatics. Hydraulics is the study and application of pressurized liquids, generally with the goal of transferring energy, whereas pneumatics uses pressurized gas to move things. Hydraulics, as applied to water, has been harnessed by human societies since the time of the ancient Romans, and we still utilize hydraulics today in a variety of situations. Central to the applications of hydraulics is Pascal's principle, the notion that pressure changes are distributed uniformly throughout a fluid in a closed system. Let me describe what this means. Imagine a water-filled tube in the shape of the letter H. There's no air in the H. It's completely filled with water. Now, imagine a plunger on the top of one of the vertical columns of our H. Recall that in our previous lecture, we learned that pressure increases with depth due to the weight of the overlying fluid. What Pascal discovered was that the pressure change due to a change in the external force, like pushing a plunger in a syringe, transmits that pressure change equally through the closed system of the fluid. So, in our example, pushing the plunger increases the pressure at the bottom of the vertical line with the plunger, as expected, but it also increases the pressure to the same degree in the horizontal segment and the opposite vertical column of our H. This is a very useful finding, because force equals pressure times area. So if one increases the area and applies the same pressure, the force generated also increases. Going back to our example, let's construct a new H, in which, in this case, the 2 vertical columns are of different diameters. Exerting a force on the smaller diameter side by pushing a plunger at the top of it will change the pressure throughout. Pascal's principle tells us that. But the force generated in the column with the wider diameter will be even greater. This phenomenon is what powers hydraulic lifts. A small force in the part of the machine that is narrower is multiplied as the diameter in the attached tubes increases. It's also how your foot can exert only a small amount of force on your brake pedal, but still manage to slow and eventually stop your massive heavy car. The field of pneumatics applies essentially the same principles, but the medium is gas rather than liquid. While liquids and gases often act in similar ways, there's another medium that is akin to a combination of the two, that is slowly and quietly revolutionizing fluid mechanics, and that's plasma. At the frontier of fluid mechanics is an emerging subfield that has already yielded some life-changing applications: plasma physics. You may have heard the term plasma before, but what is it? Is it a gas? Is it like a liquid? Is it more like slime? Well, technically, plasma is a transitional state that occurs when a gas is exposed to very, very high temperatures, which cause the atoms within the gas to ionize. Ionization, you'll remember, means that the electrons are separated from their atomic brethren, the protons. When this happens, the result is a mass of charged particles. And even though plasma is neither a liquid nor a gas, many of the principles of fluid mechanics still apply. Plasma is essentially net neutral in its charge as a medium because the positively and negatively charged particles are present but unbound and they cancel each other out. In fact, a recombination will spontaneously occur when the conditions for ionization don't persist. For the majority of applications of plasma physics, we can treat plasma as a fluid of charged particles in which electromagnetic forces are accounted for, so that's why fluid mechanics still apply. We come across plasma in several ways in our daily lives. The extreme heat of a lightning bolt temporarily ionizes the air around it, producing plasma. But I'd like you to appreciate that plasma is actually the dominant material state in the universe. The sun and all the twinkling stars in our night sky are composed of plasma. Because fluid mechanics applies to all of it, it's among the most important fields of science. Closer to home are the so-called plasma screen TVs available at the electronics store. Inside the screens of these TVs are millions of tiny cells or pixels that contain gases like helium, neon, and xenon, combined with a minute amount of mercury. An electric current applied across the cells ionizes the gas mixture, producing plasma. The free electrons in the ionized gases, the plasma, then interact with the mercury to produce small amounts of UV photons. These UV photons energize phosphor screens within the pixels to produce visible light. So you're benefiting from plasma physics every time you turn on your television. And think about the extraordinary future in which plasma physics could bring us new sources of energy, new medical technologies, or new efficient fuels for transportation. An especially beautiful example of plasma is the aurora borealis, also known as the northern lights. Perhaps you've seen pictures of it, beautiful, wispy, iridescent streaks of blues, greens, and reds across the night sky. It turns out that the aurora borealis is an example of Mother Nature painting our skies with plasma, as the lights are generated by the ionization of oxygen and nitrogen atoms in the upper atmosphere. Ionization of the oxygen atoms typically renders a greenish color, while ionization of nitrogen renders it red or blue. And the electric charges of the northern lights cause them to line up with the Earth's magnetic field, which is why we see them in the far north near the magnetic pole. As the plasma is electrostatically charged due to the separation of positively charged protons and negatively charged electrons, it has certain fluid properties that make it unique among the other three material states: gas, liquid, and solid. Sometimes it's hard to see the point of studying certain esoteric topics like airflow or the compressibility of different material states. But until we understand the basic physics, we can't improve upon them, and we can't harness the powerful forces in our world to do our work for us. And fluid mechanics clearly has many applications, some of which we encounter every day. So although engineering seems to have the most obvious applications of all the scientific disciplines, it wouldn't exist without the vast and growing body of knowledge that theoretical physicists, evolutionary biologists, organic chemists, and all the other scientists in various disciplines provide. What's more, now that we know that much of the universe is actually made up of plasma, solving the remaining mysteries of fluid mechanics has become even more critical. What can we infer about the universe with this knowledge in hand? To begin to answer that question, in our next lecture, we're going to step off the planet, out of our own atmosphere, and begin the exciting exploration of the vast space around us. And that journey begins when we investigate the very beginnings of our plasma-filled universe, starting with a Big Bang.